these from compiler classes. It could be loop optimization techniques can also be employed by malware writer to obfuscate the code. So in this particular case, we are changing the way the loop iterates over a block, data block. So generally, in this particular case, let's say K indicates row and K indicates column. So for the first row, all the columns are traversed. Then for the second row, all the columns are traversed. For the third row, all the columns are traversed, and so on and so forth. Now, in this particular case, rather than we going by, we go the same way, but rather than going row column wise, we are going block wise. We traverse the rows and columns of this block, then rows and columns of this block, then rows and columns of this block, and rows of columns of this block, and so on and so forth. Now here, it looks as if we are running a loop, a four-nested loop, and it might look more complex, but actually it is implementation of the same code as this, but the way the loop elements, matrix elements are being traversed is changed. Or we can go diagonal, correct? So we can change the way the matrix is being traversed, a 2D matrix is being traversed, and make it look more complicated or simplified as. So this code can be simplified to look like this, and this code could be made to look more complex by using this strategy. Now, in case of loop unrolling, the same loop is actually being divided into a sequence of 2 loops. In this particular case, you can see I starting from 2, and then it's being incremented by 1. Is that right? So it appears as if that we are just looking at the even indices and not the odd indices. So odd indices are being taken into consideration by adding another statement. So here, the loop iterates over each element of the one-dimensional array by making the iterator by incrementing iterator by 1 and writing only one statement in the loop. Here we are making the iterator increment by 2, but writing 2 statements in the loop. So this looks far more complicated than this loop. Here it becomes easier for us to understand what is happening, but here it becomes slightly difficult for us to understand what is happening. Or loop can be divided into 2. Here, this is a single loop containing 2 statements. Now, this has been written as 2 single loops containing one, each of which is containing a single statement. Loop can either be blocked. Basically, we are actually changing the way the elements of a matrix 2-dimensional or 3-dimensional matrix is being traversed. Here, we are actually changing the way the iterator is incrementing and changing the number of statements in the loop. Here, we are breaking the loop into 2 different loops. So the first loop is actually catering to some instructions in the loop, and the second loop is concentrating on the rest of the instructions in the loop. Now, we can also make a program look more complicated by addition of what we call opaque predicates. Opaque predicates, they look very complicated, but they are actually some kind of mathematical formulas which are either true or which are either false. Okay. So if we write it like this, this means we are using a predicate which is always true. If you're writing it like this, it means we are using a predicate which is always false. If you're writing it like this predicate, it depends upon, it might evaluate to true or false. For example, if we want to execute a sequence of statements, statement A, B, and C, this is the easiest way to write it, and this is the easiest way to interpret what is going on. Then I can also write it like this, statement A, and then I'm writing a condition which I know will always be true, and statement B. Otherwise, I'm writing some dummy code which I know that I'm not going to execute it, so I can make it as complicated as possible, and then statement C. Or I can use a predicate which is always false. The dummy code should come here. Okay, there's a then dummy code, otherwise statement B. Now, in this particular case, if you look at the third one, it doesn't matter whether the predicate is true or false. Doesn't matter whether the predicate is true or false, because in both else, if and else condition, we are executing statement B. Now, quite possible to make it look different. Statement B may be rewritten by using equivalent code. These are some predicates. You can check it out. They are all from the mathematical properties. 7y square is never equal to x square plus 1. Why it should be so? Well, you can check it out that this is always true. X is greater than or equal to 1 or x is less than 10. Well, this is always going to be true because x is either going to be less than 10 or it is going to be greater than or equal to 10 because x is an integer. Multiplied by x plus 1 mod 2. Now, actually, if x is odd, x plus 1 will be even. Or if x is even, x plus 1 will be odd. So naturally, if one of these have to be even. So if divided by 2, I know it is going to be 0. So this is always going to be false. So these are some predicates. This is always going to be false. Similarly, these are 3 consecutive numbers. Now, if you look at any 3 consecutive numbers, one of them has to be divisible by 3. So it is always going to be true.
Hello.
Similarly, opaque predicate can also be set using pointers. So we have a method P, and there are 2 global pointers G and H. And G is pointing to the dynamic structure capital G, H is pointing to the capital dynamic structure H. And okay, so basically what we are going to say is okay, we can have 2 pointers in which let's say these 2 pointers are pointing to a linked list in such a manner, which is circular kind of linked list, such a manner that G ka next ka previous is again equal to G. Or G or H may be pointing to 2 different nodes, so we know that G can never be equal to H. So we can set opaque predicates using pointers. Now this will be very difficult for static analyzer to know whether these pointers are pointing to the same place or not, because only a dynamic analysis we may be able to know whether the value is going to be true or false. So the idea is that malware writer is going to use some statements which he or she knows is always going to be true or is always going to be false, and accordingly manipulate the control flow transformation of the program. This is another example. Now here we are using this 7y square is equal to x square plus 1. This is a predicate, we talked about that. Okay, 7y square equal to x square plus 1. So 7y square is never equal to x, 7xy square is never equal to x square plus 1. Okay. So now what it is doing here is it has created 2 threads. This thread is actually creating a random number which is r into r, which is equivalent to x into x square. This is equivalent to 7y square. Okay. And S is run, and then T is run. Okay. So now R is a random number, X is another random number, and here we are squaring X with a random number with itself. So it is again a kind of a form of X square. So this is a form of X square. This is a form of 7y square, and we know that 7y square is not equal to X square plus 1. So we are saying 7y square minus 1 is never equal to X square. So we know that this predicate is always going to be false. But if the compiler, if static analyzer or the person who is analyzing doesn't know that this predicate is always going to false, he will be looking into if condition as well as else condition to understand what this program will be doing. But actually, all he has to look is into the else condition, because whatever is written in the if condition doesn't make any sense. That's the point. So opaque predicates can make it very difficult for analyzer to know what is happening, because some of the control flow path may not at all be visited by the program because of these opaque predicates, because these predicates are either going to be true or they are going to be false. So these predicates can also be used to seemingly make to implement a sequence of to maintain the order in which the sequence of instructions should be executed. So we divided the sequence of instructions. This was a sequence of instructions. We divided it, partitioned it. So and then we are writing a predicate. If it is true, then we have to execute it, because this predicate is always true. Always this will be executed. Whatever written here doesn't matter. It can be written something else, but actually what is being executed is S1 to Sn and then Sn plus 1 to Sn. Okay. Now this particular predicate is neither true nor false. It will depend upon the input. Okay. But the way it has been written is that this set of instruction is equivalent to Sk plus 1 to n, and this is also equivalent to Sk plus 1n. So this is again going to execute the same set of instruction, S1 to Sk, followed by Sk plus 1 to Sn. But naturally, these instructions syntactically will look different from Sk to Sn. They are equal to that, but they are not exactly the same. So this is based on a predicate which is always true, which is based on a predicate which may or may not be true, which may be true or which may be false. And this is again a predicate which is always but in this particular case, the set of sequence of instruction is not equal to the sequence of instruction as written over here. Now, code is consisting of the sequence of instruction. It is easy to understand, but if this has been made to look complicated by using this obfuscation or this obfuscation or this obfuscation, it becomes difficult for analyzer to understand what is happening. Similarly, in this particular case, this is a loop, and this loop will change the value of k, again check whether the condition on k is true or false. If it is true, it will again enter the loop and so on and so forth. So again here we are using a predicate which is always true for k and j. Okay, so depending on so whatever k and j is value, j is actually derived from k in such a manner that this predicate is always true. So this loop will run. This will have a false condition, but this will not have any impact on the analysis. But the problem is the moment a false condition is added, the code will become bigger because there will be some dummy code, and analyst has to look at this dummy code also, because it doesn't know whether this code uh, flow, this path, so this control path will be executed or not. Now here we are showing it only as one level of nesting, but it can be again broken down into multiple level of nesting. This is yet another one. Again, this is a predicate which is always false. So only on false it will exit. Okay. Now what happens here in this? This predicate is true, comes to the loop, execute the loop, J is assigned something. Irrespective of whatever J is assigned, this predicate is always false. But this path will be executed only when K comes to a condition. K becomes the value of the K is the terminating condition. Otherwise, this loop will this particular condition block will not be executed. Unlike here, this condition block is executed for every iteration of the loop. Here, this condition block will be executed only when the loop is about to exit. So this particular path and this particular path are meaningless. But to a person who doesn't know that this is actually a predicate which is always false, it will not be that obvious. Similarly, here control flow graph is being modified. So this basic block is being divided into two basic blocks. It appears that these basic blocks are part of two different loops, but it is not so. They will be actually executed the same way. So the control comes here, comes here, and comes there. So it will be like this only. But anyhow, similarly here, this is the initial block. This block is being executed in the loop, and when the terminating condition is true, it will go out. So this again appears as if this is consisting of two different parts, but they will be executed in such a manner and that if you look carefully, the initial part of the block is executed, then this predicate is always false, so it comes here. This part of the block is executed, and then it comes here, and then it is again the loop which is being executed. Now again here, this will be executed. This is always false, so this will be executed. Again, this block is also divided into two. If you look at the right hand side, so it is going to execute the same set of instructions in the same order as this one. This looks much more complicated because this block is also broken and has been inserted at different places in the code, and this block is also inserted into different places in the block, and they are being connected by conditions. Now, if it is not known that this is always a false predicate, this is always a false predicate, it may not be able to actually visualize how this loop is being executed. Now, this we already discussed. This is flattening a program. So basically, this code block is executed, and then it may be executed multiple times, and again you exit it, then this is executed, and so on and so forth. Now here again, this is the dispatcher module. There will be some state variable which be assigned a value, and depending upon the state variable, this block, this path may be executed as many times as depending upon the variable which will be updated, and after that it will start executing this depending upon the actual implementation of the same. The only difference here will be that we need to have some kind of state variable. We discussed a program initially a similar, if you recall. So this was the dispatcher, and this was the state variable, and the state variable was in this dispatcher which particular block to execute next. We're doing the same thing essentially here. This is another one. Here we are actually dividing this block A into equivalent blocks with cloning A1, A2, AN, and B with B1, B2, BM. So it has to be executed, let's say, n number times, and B has to be executed n number times. So when n equal to 1, it will execute, it will be changed. N equal to 2, this will be executed, state will be changed. N equal to capital N, it will be executed, state will change, and again, now it will start executing these blocks. Now this code will be much bigger than this code, and it will be difficult to understand. And some dummy code can also be added to make it look more complicated. And this code may or may not be actually executed. So this is a code which is consisting of source code. Now, actually, this is what compiler does when it tries to write the equivalent code for while loop. So it is checking the condition. If the condition is not true, it will go to exit the loop. Otherwise, it will execute the loop, change the variable, and again go back to L1. So this is basically implementation of the loop. Another way to execute the same loop would be initial condition A equal to 1, B equal to 2, and then state is set to 2. At 2, when it comes again, state 2, it will check that is less than equal to 10 or not. If A is less than equal to 10, if this condition is true, it is 6, which is exit the loop. Otherwise, the state is 3. State is 3, it will execute this and again go to state 5 or 4, depending upon this condition. And this is how the same loop is being implemented by using flattening. Now, control flow obfuscation can also be done by using the way the libraries are being used. Now, library names cannot be obfuscated. So, the same library can be copied and renamed to some other name and use that library name to make it difficult for people to understand what is happening. And this library can be part of the code itself. So in fact, some of the Windows malware, they use old PowerShell script to bypass the new PowerShell script mechanism. So they are actually built in with their own PowerShell because the new PowerShell script may not actually run the old code. So they have their own new old PowerShell script interpreter along with their script so that this can be run. Okay. Now this is interesting. So what exactly is being done here? Let's see. So what is again compiler will okay. So it will assume that there is a, let's say, virtual processor, or there is a hypothetical processor, but there is a different processor, and this processor has, let's say, 4 registers instead of 16 or 32. And then there is a instruction set of these. This processor can also be devised by the malware writer. So instead of move instruction, it can have read from RM, read from memory, WM, write to memory, and then they can have different opcodes. So what it can have a so actually the source code will be compiled to intermediate code of this compiler of this processor, and then there will be a module which is going to read this code intermediate code and create the target code for the processor. Instead of delivering a executable file, it is going to deliver a intermediate code file along with an engine which can translate this intermediate code to the actual target code of the machine. Now, I don't know how many of have you coded in Java, but Java does it by you converting this into Jimple or Shimple. It has got 2 or 3 intermediate code representation. Now, the problem with the intermediate code representation is that unless you know what is the architecture of this hypothetical processor, it is difficult, and what is the say it is difficult to know what is happening here. And advantage of from the perspective of the malware writer is that they can have many different intermediate codes, many different kind of hypothetical processors, and different engines. So your program will consist of a file which is sectioned into intermediate code of different types, and then engines for each to translate this intermediate code into the target code. And malware writer know what it is doing, and it can actually recreate the correct binary for that particular target machine. It will slow down the execution, but as I said, for malware writer, the main impact would be in infecting the machine rather than whether the machine is infected in 10 seconds or 20 seconds. It doesn't matter. To make it faster, they can actually create a table to convert this intermediate code to target code. So this is the intermediate code, the equivalent target code will be this. This is the intermediate code, convert this into target code like this. So they can have a table for interpretation, which can make it faster. Now in this particular case, this looks like some complicated operation, but actually here it is some mathematical expression which is always going to be equal to 1. Okay. And for example, I can say 7 plus 2 mod 8. I know this is always going to be 1. So I'm multiplying it by something which is always going to be 1. So here it looks even more complicated, z equal to l plus 1. But if you look here carefully, p is always equal to 2q and q is always equal to p by 2. So naturally, they both are. If I divide these two values, it is always going to give me 2, and 2 divided by 2 is always equal to 1. Last, we are coming to where the data is actually stored. So these are data transformation. The first one is split variable. Scalar can be converted into objects. Easiest one is making 2-dimensional vector or 3-dimensional vector. Convert data to procedures, change encoding, change lifetime of the variable. So either you can divide or you can aggregate, merge scalar variables, modify relations, etc., etc. So in this particular case, we are changing the encoding. How we are changing the encoding? Okay. So here we are taking a array. The index is starting from 1 to 1 onwards. Again, we are doing here the same thing. We are using a array. But this array here, the size of the array is 25. But we know that we are not going to use entire 25 locations of the array. We are going to use only certain locations of the array. And these are corresponding to the same locations here. If I say k equal to 2i plus 5, here when I equal to 1, so what? Let's say it's 1, 2, 3, 4. I equal to 1, k will be 2 into I, that is 2 plus 1, 7. So I'll be storing 1 at 1, 2, 3, 4, 5, 6 at 7th location of this array. Then I equal to 2, k will be equal to 9. So then I'll be storing it at the 9th location. When k equal to 3, so other locations what is stored doesn't matter because we are not interested in that. It could be garbage. So another way is that we can actually combine 2 or more data of the original representation to, we can compact them together in the new representation. For example, if it's an array of characters, I can represent it as an array of integer where I know that this character is stored in the lowermost byte of the first integer, this character is stored in the next byte, this character is stored in the next byte, this character. So all these 4 data are actually becoming one new record of the new representation. Similarly, next 4 byte will be stored here. Next 4 byte will be stored here. It makes it difficult to understand what is happening, and access of the and dealing of the variable also becomes slightly difficult, and code becomes unreadable. So in this particular case, we are using local variable. We can represent them. We can replace it by a global variable which is being accessed, or we can use local variables instead of global variables. So we can use either global variables to exchange data between the procedures, or we can use local variables and pass them as parameter to exchange the information between two processes. So here 16-bit data can be stored as two 8-bit data, and then you have to change the procedure by how you are adding or subtracting or multiplying or dividing the data. Now this is an example of so these Boolean variables A, B, C. A is actually represented by A1, A2, B is represented by B1, B1, B2, and C is represented by C1, C2. If either of A1 or A2 is true, then it is true. If both of them are false, then it is false. Okay, so now we have to have a representation also. So we are saying that if in case of A, if one of them is true, one of them is, if they both are different, then it is true. If they both are same, it is false. In case of B, we are saying that both of them are 0, it is false. In case of C, we are saying that if both of them are 1, then it is false. And then this expression A and B will now change in this particular case, and it looks more complicated now. Unless someone knows how we are encoding the same Boolean variable, true, false, true, each Boolean variable is actually being replaced by two integers. And how these integers are set, or these integers can have value between 0 and 1 only, and how they are set to 0 and 1 will determine whether that is to be interpreted as true or false. So if we change the definition of how true and false represent, well, then these expressions will become very difficult to understand. In this particular case, we are doing the scaling of the parameter. So in the original function, we are passing n, and in the revised function, we are dividing n by 3, and we are also passing the we are passing two values, which is n divided by 3 and the quotient and remainder when n is divided by 3. And accordingly, the function will now change. So in this particular case, what we want to do is we want to recognize the set of regular expressions. And this is how this has been encoded. If n equal to 1, then initially I equal to 0, we will check whether this is equal to A. If it is equal to A, then we set k equal to 0 and go to L6. And then again at L6, we again check something and do it. So this becomes very difficult. So this table of what we want to do can be encoded as statement, go to statement, and instruction label like this. So this is a very complicated code. So instead of creating a string of an array of strings, which is data, we are actually writing a complicated code to generate that array. So depending upon what is the value of n, so if n equal to e, then this function is going to return CCB. If I pass n equal to 4, it is going to return XCB. So it is going to return the same thing. I could have done the same thing by writing this table, but then it will be very easier for people to know what exactly is the data that my code is using. So by generating my data on the fly, by writing a code which looks very complicated, it becomes difficult for people to know what exactly is happening here. So in this particular case, to create a 64-bit variable, we are using two 32-bit variable. So, and then we are writing the equations to how to get the value of 64-bit variable by using two 32-bit variable. Or, as I told you, we can merge many variables into an array. I told you that in terms of characters, but it can be applicable to other situations also. This is interesting. So this is a kind of one-dimensional data. This can be treated as a one-dimensional data. I can rewrite this as a two-dimensional data by creating two rows, and I know how my data is stored here. So all my even indices are stored in the first row, and all my odd indices are stored in the second row. Now, in this case, I'm actually merging the two one-dimensional data to create another one-dimensional data, but I know how I'm merging them. So I'm having one data from B, and then two data from C, then one data from B, two data from C, and so on and so forth. So it becomes, I know how my data has been merged, but if someone doesn't know what has been done, they do not know how I'm accessing my data. So this is another one, but in this particular case, I'm doing first five in the first row, next five in the second row. I can make it more complicated also. I can actually create a random number generator which is going to generate the number from 0 to 9, but then I can actually generate I can say that the first index is actually containing 8, the second index is containing D3, third index is containing D7. I can actually arrange them in different order. So this is how array is being transformed. So this is an array which consists of 9 elements, which has been actually converted, 10 elements, 0 to 9. This is now converted into two arrays containing 5 elements. And here, we know that if index is 1, then we have to access it from A1, otherwise we have to access it from A2. In this case, we were actually merging the arrays. Now here we are actually transposing the elements. Okay, I was just going to explain this one. Now, in this particular case, this is the complete source program, and this source program is consisting of sequence of instructions. These sequence of instructions are not very sensitive. This is what I do not want people to know what is happening. I want to keep it secret. So now these blue boxes are showing are showing the code blocks which can be run in public systems, but this has to be run in confidential. So what can be done is that we can have two type of devices. One is normal computing device, another is secure computing device. Blue code can be run in normal computing devices, but secure code will be running on secure computing devices. Now, the secure computing devices could be something to your command and control server for botnet, so that no one knows what is happening. It could be something in cloud, which is under the control of the malware writer. So part of the code is running on the host machine, and the part of the code is running on the remote machine. So it is very difficult to know what is the complete code doing. This is some of the instructions. If you have any questions, we can continue with that. And Vikas, you can share these slides with the participants. And if you
Sure, ma'am.
have,
Thank
okay,
you
I
so
have
much,
not
ma'am.
written my email address, but someone can add it to the
I will share
presentation.
with them, ma'am.
Okay.
So
So if there are any questions,
participants, if you have any question regarding the obfuscation techniques ma'am has discussed, we may ask her. Put
so for
your
example, you can get this particular code. So what the
yes,
person has done is this example is available here. So printf has been renamed as 0L0 put char 0L0 exit 010. And now if you look at this code, it is very difficult to understand what this code is doing. So even for human eye, through this is a C program, it is very difficult to know what it is doing, because if you look at these strings, they look quite similar. 010, 0L0, 0 O10, O10, this is O10, OL0, so QLQ. So they look so similar that it is very difficult for you to know unless you replace it, write a code to replace each and every string. Then only you will be able to know what this code does. If you have any questions, we'll continue. Otherwise, we'll call it a day. Any questions? Okay, you might not have any questions because right now it might look too heavy, too boring to. So you can email me the question and I will try to answer to the best of my ability. So have a good day. Vikas, can I leave?
yes, ma'am. Yes, ma'am. If there is no question, we may. Yes, ma'am. Now there is no more question in the group. Thank thank you so much, ma'am. Sir, ma'am,
Okay, take care.
one question is there, ma'am.
Yes, please.
It is obfuscation technique can evade only signature-based malware detection?
Yeah, it is actually used to evade signature-based malware, but it is also used for making it difficult for people to understand what the code is doing,
Yeah.
because they also try to sometimes confuse disassembler, and the disassembler may not give you the correct output. So you might actually analyze completely different code which was meant to be.
Yeah.
So it is, yes, difficult.
So, any more questions from your side, participants? If you have, you may ask. Yes, I will share the mail ID. I will share surely. So, thank you so much, ma'am. I think
Thank you.
we have explored various dimensions of obfuscation techniques, and we have now exposure to all the mostly all the techniques. Even we were unaware about this, how coding can be used to manipulate or means attain the obfuscation. So, I hope this discussion has basically opened the area for their research, and they've got to know what different approaches are. So, thank you so much, ma'am. I will share your mail ID with them if they want to connect with you. Hello.
Okay, I'm just writing my email ID in any case.
Yes, ma'am. I will share with them, ma'am. I'm just sharing with them in the mail ID itself, in the chat box itself. So this is the mail ID ma'am has provided. You may connect with ma'am. So with this, I think the session is closed now. Uh, we thank you. We all
Thank you,
thank you,
everyone.
ma'am. Yes, and we thank you all the participants who have been there in the throughout the session. And thank you so much, ma'am, for your time.
Okay, so have a good day.
Good day to you,
I'll be
ma'am.
leaving the meeting now.
Yes, ma'am. Thank you, ma'am. So, participants, the next session will be starting from 6 o'clock, and will be taken by Mr.